Hi everybody, it's Dr. Chabot, and in this video we're going to learn how to calculate the electric field from continuous charge distributions. So we have the discrete equations where if we have just multiple point charges, and if we have multiple point charges, we know that we have the individual electric field from one point charge is going to be equal to KQ over R squared, right? And that gives us that value for that electric field. And then if we want to get the total electric field, then we add up all of our vectors for each of our point charges. So Q sub I over R squared, R sub I hat, and they all have their own direction, and so you have to do components and all that stuff. And so what we actually see is that this ends up being that the E total in the X direction is equal to the sum over I of all of the X components, right? Of all of the E sub I X components. So you have to add up all the X components separately, and in the Y direction we have to add up all the Y components separately. So we have to do components whenever we're adding vectors. So when we're doing continuous charge distributions, that is when we now instead of take a bunch of discrete charges, but we instead talk about having an infinite number of discrete small charges, we're still going to be in vector land. So we're still going to have to do this. So if we make this analogy now to a continuous charge distribution, then what we use is the idea of a tiny, tiny, infinitesimally small point charge. So dq, here I will write down over here, I will make some space to make a nice analogy going. Over here we had q sub I was just our point charge. Here we're going to have dq, and the D just makes it small. This is a tiny bit of charge. It still has units of Coulomb. It's just a tiny little bit of charge. It's not the derivative of Q or anything like that. The D is just saying that I'm taking now a tiny little bit of charge. And it's going to make a tiny electric field. And the tiny electric field from that dq, we're going to call dE. Again, the D is just making it small. So dE is going to be equal to K dQ over R squared. And so we can see that we've done this direct analogy by just making the electric field and the charge small by adding the D in front of it. So that's going to allow us to transition from the discrete addition world into the calculus world of continuous sums. So we have here dE equals K dQ over R squared. That's the same equation as we had before, except for now we have made the amount of charge small, a dQ, and therefore we have a small electric field, a dE, that is created from it. If we want to get the total electric field, we're going to do the same thing. We're going to add all of these up. And so we're going to have a continuous sum of all of our dEs, which is the same thing as an integral. So that's what an integral is. It's a continuous sum of all of our dEs. So we're going to add up all of, and I'm going to leave it here as our vectors for now, because a continuous sum over vectors is still a sum over vectors. So we're still adding vectors. And so very importantly, we still need components. So we still need to do this in components. So we're not actually going to ever integrate to get the total electric field without worrying about components. So very importantly, we then say that E total in the X direction in the continuous world will be the sum over all the X components of our small electric fields. And the E total in the Y direction, as you might guess, is the sum, the continuous sum, the integral, over all of the Y components. So we have to make sure that we're still using components. Now, how are we going to get a dq? So let's say that we give some situation where I have an object and it has some total charge q, and the question then becomes, how do I get dq to be something I can integrate? The other variables here are r, right? So r is a spatial variable. So like the idea of, for example, something that goes as 1 over r squared dq, that's going to be our question mark. What do we do with that? So this is very similar to when we learned about moment of inertia, and we had to take our densities in order to put mass in terms of spatial distances, like volume or area or length. Here we're going to do the same thing, but we're not going to use mass densities, we're going to use charge densities. So we're going to here use our charge densities are going to relate charge to spatial things, so spatial lengths. So things like distances, 1D distances, 2D areas, 3D volumes. That's what I mean by spatial quantities. So charge densities relate charge to length and allow us to then write that dq as something useful. So we're going to have different dimensions here. We're going to have one dimension. We're going to have a charge density lambda, which is a linear charge density. And this linear charge density means literally that it is charge per length. So that's going to be coulombs per meter. And that's going to be something that allows us to then put dq in terms of lambda. So in the 1D world, then, if I wanted to get dq, I could say that dq is going to be equal to my charge per length times a tiny bit of length. So that's what I would get for my charge. If we just think about this, think about what density is. I have something, say like a bar, and it has some charge per length. It has some lambda, which is my coulombs per meter. If I take some little bit of this is a tiny bit of it, then it would have a tiny little bit of charge. How much charge it has depends on its length of that tiny little bit I took, right? And so the tiny bit dq has some length to it that I'm going to call ds, just some tiny length. And so I can then say dq is equal to my charge per length, which is my lambda, times my tiny bit of length, which is ds. And so that's going to be my 1D summary of how I can get dq written in terms of something useful. And then we'll do a couple examples in 1D to see what that looks like. Quickly, I am going to write down what it looks like in 2D. So in 2D, we would have a sigma, which is a charge per area. So a charge per area. And so then we would actually be able to write out a dq here. Dq would be equal to sigma times some tiny little bit of area. And so that's going to be what we might use if instead of we had a long bar, we have a solid flat plate or things like that. And then lastly, we're going to have our 3D where we have a rho, which is a charge per volume. And so we can write dq as the rho, the charge per volume, times a tiny bit of volume. So those are our different dimensionalities for how we get our dq from a density. We're going to start with just 1D to practice our problems. So let's go ahead and see what that might look like. All right, so here's the example we're going to work through. We have a line of charge, uniform charge distribution to start. We'll see later what happens when you have a non-uniform charge distribution. So uniform charge distribution, a length L, a charge Q, and we want to find the electric field at point P, which is a distance D from the left end. Okay, so let's dive in. Remember that we're still adding vectors. So we are still adding vectors. So it's actually going to be very similar steps to everything we've done when we just had point charges. So we still want to visualize the vectors that we're adding. So now if we look at the steps where we draw the picture and we visualize the vectors. So what we're going to do is we're going to draw a tiny little bit, kind of purposely randomly located, we're going to draw a tiny little bit of charge dq onto this line. And when I draw my dq onto that line, again, I picked kind of a purposefully random location, not the very far ends or anything like that, because I'm going to eventually want to add up all the different dqs along the whole bar. So I'm kind of just imagining a representative dq. And that dq has some length here. And that length in this scenario is going to be ds, very generally speaking. But notice that ds, because we're along the x-axis here, can easily be written as dx in this case. So I can see that dq then would be my tiny little bit of charge is going to be my charge density, lambda, times my dx here. So we'll come back to that. But that's our visualization of ds. We also want to remember what equation we're working with, right? Our fundamental equation is that the magnitude of dE is going to be equal to k dq over r squared. So what is r squared now that I have this long object? Well, very specifically, r squared, or r points, or is the distance from dq to the point you're finding the electric field at. So the point you need. So in this case, I'm going to have that my r is this distance from point P to ds, and notice that it's variable. So it's variable, and it changes. In this example, it's variable and it changes with a different dqs. So each dq on this bar is going to have a different r. And so now what we want to do is maybe say, okay, well, what is the electric field created by this dq? So if we want to visualize the electric field created by this little dq, it's a uniform charge distribution, total charge Q. We can assume that that's a plus Q. And so my electric field is going to point away from that little dq. So I'll have an electric field that I'm visualizing that is pointing away. I'm calling it dE as opposed to E because that is just one electric field from one dq. I can then say visualize another dq. Let's picture a dq here. And since they're all on a line, I can see that that dE is also going to line up. So all of my electric fields point to the left. And so I can see that my net electric field in this case is just to the left in the negative direction. So that's going to become important once I start navigating the math of some of this. Okay, so I visualized my vectors. I know the little tiny point I'm talking about. I have this distance r visualized. So now let's work this out. We're going to first write out our magnitude of the vectors. So the magnitude of dE is simply going to be equal to k dq over r squared. Now note that r in this scenario is simply going to be equal to x. I'm going to explain why. You're like, well, what about d? Isn't it d plus x? Well, we started at point P at the origin. And so r is equal to x because the distance from point P to my dq is in fact just going to be equal to x. The d in this case is going to show up in the limits. So that's where a good picture goes a long way. So rx is just r squared, right? And that's only in this example, right? So every example is going to be different, and you're going to have to sketch it out and figure out what your r is. And then dq, as we saw before, can be written as lambda dx over x squared. So now we have something that's looking like we can definitely do it. Lambda is uniform, so we can go ahead and write this as k, and lambda is charge per length, q over L. It's uniform dx over x squared. Perfect. So this is now our magnitude. This is just a magnitude of the vector. We now need to do components. Now, in this first example, I picked a very simple one where there are no components because it's not pointed at an angle, but we're still going to pretend we're doing the step of taking components. Remember to ask yourself if it's plus or minus, and then if you need a sine or a cosine. And in this scenario, I don't need a sine or a cosine, but I do need a negative sign. So I can see here that my E total is equal to my total in X only. And so that's going to be equal to my negative times my magnitude, and these are all my DEs. So DE X, and then times my, in this case, no sine or cosine, or if I did want to use one, I could use the cosine of 0, right? So maybe I'll put that in just so that we can see that I am, in fact, doing components in this step. So I have to do that before I integrate. And so then now we're going to just add everything up. So we're going to add by integrating. And if we add things up by integrating, now I can get that my E total in the X direction is going to be the sum of all of my little electric fields in the X direction. I'm going to bring that negative sign in, so negative times the integral of this k q over L dx over x squared, and that cosine of 0 is 1. So now I have something I can actually integrate, and I have to think about what the limits are going to be for this. And so to integrate, we want to add up for the limits. We're going to take from the left-hand side of the bar to the right-hand side of the bar. We're going to say, okay, x at the left-hand side of the bar is d, and at the right-hand side of the bar, it is d plus L. So the limits are picked so that you add up the dE from all the dQs on the object. So your limits essentially encompass the object so that you're taking up all of those dQs. And so then at this point, we're just able to solve it. And so if we solve this, we end up with this constant negative kq over L. Integral of x to the minus 2 is equal to minus x to the minus 1, so kind of bringing that up like so, evaluated from d to d plus L, and then we simply get here, and again this is in my x hat direction, and so I get negative kq over L, and I'm going to make that positive because of these two negative signs here. And then I'm going to have 1 over d plus L minus 1 over d, all in the x hat direction. Awesome. So there I found my electric field. I've done the same things I've done in the past. I've visualized my vectors, I've written out the magnitude, I found the components, and then I added them up. And in this case, I'm just adding them up with the continuous sum, which is integration. All right, so we're going to do one more example in this video, and then we'll have other opportunities to work through many more examples as well. But I also want to show what it looks like for an arc, for a one-dimensional arc. And also, I'm giving us a non-uniform charge density. So this will allow us to kind of see all aspects that might come into play. And you'll notice that it's going to be the same steps that we usually do. So here we're asked to find the electric field at the origin, which is at the center of this circle, this arc. And theta is defined in the kind of typical way from the positive x-axis. The arc has a radius r, and this non-uniform charge density given by A sine theta. So here's where we have to visualize the vectors. So we must visualize the vectors first. This is always going to be the first important step, and this problem is great because it shows us why. First, in order to visualize the vectors from different little DQs, we need to go ahead and visualize the charge distribution. So this requires us to visualize the charge distribution. So what I mean by that is A sine theta is not always positive. Sometimes I have negative charges here. So A sine theta is actually going to be positive only when y is positive, right? That's how sine theta works. Take a second to think about that because we're going to be doing a lot of problems that kind of rely on that visual, right? Sine of theta is positive whenever it's in the first or second quadrant, but it's negative when y turns negative, right? And so the charge distribution is like this. And so if we start to visualize what the DEs are from each little thing, then we're going to have to, get some symmetry there. That's going to allow us to not have to do all of our components. So what I like to do is, again, just sort of pick a purposely random DQ, and then picture the electric field from it. But when it's an arc, you kind of need to do it for each quadrant. So for this, I might also pick a DQ over here in that second quadrant. And then I'm going to picture its DE. And so then its DE is going to point away from it because those are both positive. But now I have to move down to these lower quadrants. So let's say I pick a DQ over here. That DQ is negative. And so now my electric field's actually going to point towards it. So that's another DE. And then I can pick, lastly, I can pick another, say, DQ here, and it's going to also be negative and have a DE that points towards it. So we visualize all these different vectors, and in this situation, right, the net electric field will be downward in the negative y hat direction. So I basically I've made my life easier because I only need to get my E total in the y direction, which will be adding up all of my DEYs. So I've just basically made my life easier. I visualize the problem. I know which way my electric field's going to point. And I can now kind of dive into some of the math of it. So we want to write out the magnitude. So the magnitude of DE is, as always, going to be K dQ over R squared. So now let's think about what all of these are. First, let's think about R squared. R is going to be the distance from the DQ to the point I care about. So from the DQ to the point I care about, in all of these scenarios, R is going to be my full radius of this arc. So here we actually have that R equals capital R, and it's actually going to be equal to a constant because all my DQs are equally spaced. So that's a nice thing about arcs, actually, is that that's the case of what we have for that constant in that R squared. So the R is not particularly messy in that scenario. And so what we have then for DQ is where we want to be a little bit attention to detail. And we don't want to just say lambda dx because we don't really have an x-axis and it's curving around. So DQ, which is equal to lambda ds, S now is a tiny arc length. So ds is a tiny arc length And if we remember our arc length, s equals r theta, then a tiny arc length, ds, is r times a tiny theta. So our arc length is ds equals r d theta. So we could write dq as r lambda and then times r d theta. So now we can bring this all together and write out our magnitude of dE. And again, this is not what we're integrating. This is just the magnitudes of all these lines, the lengths of all these lines. We haven't done the components yet. So we have k, and then my dq, lambda r d theta, all over r squared, which is capital R squared. And so then that gives me here what I'm ready to use for my magnitude. I'm going to rearrange it a little just to take out some and simplify some things. We can see that one of my capital R's cancel, so I have k over capital R. Lambda is a sine theta, so I'm going to write this as ka, and then I would have a sine theta d theta. So I've plugged in for lambda at this point, and that is my magnitude. So this is my magnitude only. So I'm going to say this all the time, that when we are in vector land, never forget components. So don't forget your components. It's tempting to just say, okay, I have this thing, sine theta d theta. It looks like I could just integrate it and I would get a total, but you're adding vectors, so you can't do that. So don't forget your components. You're going to need to have here that we have already decided it's only the e sub y's that we care about. So our dey, notice that it's a plus or minus. It's going to be minus because it's pointed downwards, times the magnitude of dE, which is what we found above. And then I now have to decide if I'm going to be using sine or cosine. Well, I want the y component, so I am going to be using sine of theta in order to extract that y component from this. So if I have this here, I can plug in for everything, and I can say negative Ka over r, that's all a constant, sine theta d theta, all times sine theta. So I'm going to end up with something that is a sine squared function. So I can write my E total at this point. E total in the y direction, which is the only E I have, is going to be negative times the integral of Ka over r, that's a constant, times the sine squared theta d theta. And in terms of the limits now, notice that I didn't plug in for, sorry, before I go to the limits, notice that I didn't plug in for sine theta. We leave these because we're integrating with respect to theta, so we can leave these as the sine of theta. We don't plug in for the sides of the triangle. We only do that when we're not allowed to have the theta in the answer or in the integral, but here we're actually integrating with respect to theta, so the sine thetas stay. Now the limits here are going to be the limits of theta, so the limits are going to be for theta because we're integrating with respect to theta. And since we have a full circle, we're going to just integrate around the full circle from 0 to 2 pi. And so if we go ahead and do the integral of sine squared from 0 to 2 pi, that actually just ends up being pi. It's kind of a nice integral. So we have here that E total in the y direction is equal to negative Ka over r, and then this integral, sine squared theta d theta from 0 to 2 pi, is actually just equal to pi. And all of this is in the negative y hat direction, and so that gives us our final answer. Notice the same steps. You visualize your vectors, and then you find your magnitudes, and then you find your components, and then you add them, and in this case adding via integrating, but you're very specifically adding your components of the vectors to get the total. This one showed us the important result of the arc length formula that will allow us to put dq in terms of a d theta and make us a useful integral that we can use. All right, so I hope these examples helped you see how we're going to start navigating some continuous charge distributions.